Hi, everyone. Welcome to the quarterly California Environmental Flows Workgroup meeting. I'm Chris Taniguchi-Kwan. I'm the chair or co-chair of the Environmental Flows Workgroup, and I'm here with Brianna Drescher, who's also co-chair of the workgroup from CDFW, and I'm a scientist from Southern California Coastal Water Research Project. Before we get started, I just wanted to let everyone know that this meeting is being recorded. And a little housekeeping, if you're not speaking or presenting, if you could please put yourself on mute, that would be greatly appreciated. We're going to be monitoring the chat if you have any questions that come up, and feel free to unmute yourself to ask questions as well at the end of each presentation. I'm gonna try to get back to my PowerPoint. There we go. Okay, so I just wanted to go over our agenda for today. We have a pretty packed agenda. So we're going to start out with new member introductions, and I just went over housekeeping. We have 3 presentations today. The first one is going to be about a new project that's just being kicked off, Framework to Flows, Introductions Among Flow, Temperature, and Biota. We're going to have a presentation by Daniel Philippus on a new stream temperature modeling effort. And then we're going to have a presentation by Claire Kuba talking about some of the work in the Scott River on applying a functional flows approach to evaluate salmon reproduction. And then at the end, we're going to have some time to do a roundtable of updates and then talk about future agenda items. So any questions about kind of the structure and the agenda today? Okay, perfect. So with that, we can maybe, if there are any new members on the call, feel free to kind of jump on and introduce yourself, say your name and what organization or agency you're from, and then we'll get going.
I'm Melina Watts, Safe Clean Water Program in Los Angeles County.
Great. Welcome, Melina.
I'm Claire Koba, affiliated with UC Davis and currently a postdoc at Yale. I'll be giving one of the talks later today.
Welcome.
I'm Laura Jansen. Oh, sorry.
Sorry, Laura. Go ahead.
I'm one of the other presenters presenting with Chris, actually, and I'm at the Southern California Coastal Water Research Project as well.
My name's Devin Burke, she, her. I'm with the State Water Resources Control Board with the Surface Water Ambient Monitoring Program.
Hi everyone, I'm Elena Celia. I'm also at the State Water Ambient Monitoring Program with the State Water Board.
Any other new attendees, new members, the work group?
Well, I guess I'm a new attendee, if not a member. I'm Daniel Philippus. I'm at Colorado School of Mines. Here for talk number 2.
I'm Krista. I work for Brianna at Fish and Wildlife, and I'm also a new attendee.
Welcome.
I am Anthony Navasera. I'm with the Department of Water Resources. I'm the drought coordinator in the executive branch and just here to learn. Thank you.
Awesome. Welcome. Anyone else? And feel free if you don't feel like speaking and introducing yourself, you can also put it in the chat as well. Well, I just wanted to welcome the new members and new attendees to the quarterly environmental flows work group. And one of the main goals of this work group is to really get different stakeholders, different agencies together that are focused on understanding environmental flows or water for the environment. At the same place in a venue, we can share information, talk about kind of the best available science and how that could be used to inform management decisions and actions on the ground. So really excited for our presenters that are going to be here today. And with that, you can get started. And so the first presentation, as I mentioned, is kind of like a kickoff introduction to a new project that was recently funded by the California Department of Fish and Wildlife, the Cannabis Restoration Program. And it's all about developing a framework or all about implementing environmental flows statewide, developing tools and materials that can make it easier to implement environmental flows across the state of California. And so I'm going to be giving you kind of a brief overview of this project, and then Laura Jansen is going to talk about a specific technical task, all about the interactions among flow, temperature, and biota. And so I just mentioned the outline of the task, and one of the key things also is we want to talk about kind of the structure and our vision for future interactions with the eFlows work group. And so what is Framework to Flows? It's essentially a statewide initiative to build capacity for implementing the California Environmental Flows Framework, also known as CEF. And for those of you who are new or who are not familiar with this framework, I'll go into a little bit more detail, high level of what the framework is. And the goal is to really make CEF, so the statewide framework, more usable, more actionable, and accessible for agencies and practitioners across California. And so this is about a 3-year project that's going to be wrapping up in February of 2028. And so just a little background, the California Environmental Flows Framework, this is co-developed by multiple different agencies, university partners, and NGOs of this environmental flows work group. And so CEF is actually one of the primary products of the California Environmental Flows work group. And essentially it provides statewide guidance for managers to develop scientifically defensible environmental flow recommendations, and it's following a functional flows approach. And so we kind of got a bunch of different scientists together to develop this consistent science-based framework, and we developed a set of tools to help implement this framework. And it's a really exciting time. So it got released in 2021, and it's currently being implemented across several programs and different projects across the state. And so I mentioned that CEF is based on a functional flows approach. And what this is really honing in on key aspects of the annual hydrograph that provides distinct geomorphic, ecologic, or biogeochemical functions. So rather than trying to mimic the entire natural flow regime, let's hone in on the most important aspects of stream flow, the different seasons and the different aspects of flow, from the magnitude, duration, frequency, rate of change across these different seasonal components. And of course, the way that stream flow interacts with the channel morphology, with the floodplain, is super important as well. And so ideally, we'll have a wide range of flows across the entire water year. And so just to give you a brief overview of what CEF is, it's broken into 3 key sections. Section A is all about thinking about natural flows. So we start out with unimpaired flows as our foundation. So what are the natural ranges of flow in absence of any human activity? And the end result are ranges of ecological flow criteria that are quantifiable metrics that should be maintained to support healthy ecosystems. And so that's kind of forms our foundation. What are the natural ranges of these key functional flow metrics? Section B is when you start to think about more site-specific constraints and considerations. So do we have poor water quality, like stream temperature concerns, physical habitat alterations, or biological interactions like invasive species that would make us believe that we should probably change or refine those unimpaired flows to account for these more site-specific constraints that are happening in the watershed that we're working in. And the end result is a refined or revised set of ecological flow criteria. And so Section A and Section B are all about thinking about water for the ecosystem, water for the environment. And you could stop there. But in some cases, in many cases, there's some balancing that needs to be done. We need to start to think about human uses of water and other management objectives. And that's where Section C comes in. So we have kind of our ecological flow needs. How are those reconciled with social values, with other management goals that are important that we need to consider? And so the end result of Section C are balanced environmental flow recommendations that support water needs for the environment, for nature, and then also water needs of people, which are equally important. And so this is kind of in a broad stroke how CEF is structured. And so through the first phase of developing this framework, we developed statewide models that predict the natural ranges of flow for Section A. And in this second phase of funding, that this new project that we're kicking off, we're actually working to develop and refine the statewide models. We're also looking at different approaches and tools where we can use in Section B when you start to think about water quality concerns. So Laura's going to talk about that. And then in Section C, when we start to think about human uses, we're developing a tool and a modeling approach to get a better handle on the impact of groundwater pumping and groundwater depletion risk. So what's the risk of drying due to groundwater pumping in a stream? And so some of the key deliverables for this new project is, as I mentioned, a set of tools to improve our ability to predict flows for fish and wildlife. And so we have 3 technical tasks that are all about refining or developing models and tools that can help us think about stream flow for the environment. Another task that we have is focused on developing an environmental flows dashboard to really track and understand where environmental flows have been implemented on the ground. What are some policy and more legal drivers of environmental flow implementation? And then where we have data, where we have gauges, maybe ecological data, to assess the performance of these environmental flows that have been implemented on the ground in terms of actual stream flow in the stream. So have these flows actually been realized on the ground and potentially in terms of ecological responses. And then the last piece in all of this, we really want to make it easier to implement the framework, easier to use the tools that we're developing. And so we're going to be developing an implementation guidance document and also a suite of outreach materials for agencies and practitioners, which includes a set of workshops that we're going to be hosting as well. And then this also includes thinking about lessons learned from the wide range of case studies that have been implemented on the ground to help inform our implementation guidance. And so ultimately, what we want to do is develop tools and resources that will help aid in implementing CEF, implementing environmental flows. So that includes tasks to develop or refine existing or new models focused on unimpaired flow, groundwater depletion effects on surface flows, and the interactions between flow and water quality. So these are 3 separate tasks that are led by the 2.1 is led by UC Berkeley, Ted Grantham, and Sarah Yarnell. 2.2 is led by TNC and USGS, and the water quality task is led by SCORP, my agency. And then, as I mentioned, we have a task that's focused on tracking environmental flows implementation and assessing performance. And we're going to be working with TNC to develop kind of a user-friendly dashboard where you can kind of visualize where these environmental flows have been implemented and look at some of the data analysis and data visualization from that effort. And then the fourth task is all about outreach and providing additional guidance. And so we're going to be developing implementation guidance, case study examples, and hosting a suite of training and outreach events as well. And so I just wanted to end this overview for this new project on our vision for coordination with this statewide environmental flows work group. As you can imagine, there's a lot of different tasks, a lot of different leads for each of these tasks. And so we're thinking that we could provide presentations and kind of update on these different elements of our tasks to the work group through these meetings and get a chance to hear from you all and get feedback and see if there's potential opportunities for collaboration or leveraging opportunities with some of the existing efforts that you all are working on. We also have case studies for some of the technical models and tools that we're developing. And so there could be potential interest to learn more about the case studies and potentially collaborate on those. And then the last piece that I mentioned are training workshops. So if anyone is interested in those, we'll keep you all up to date on when those will be and what the topics will be on. Any questions on kind of the overview? And we could also, maybe we could pause. We can pause at the end of Laura's presentation too. There isn't anything right now. So with that, I will hand it over to Laura. So I'm going to stop sharing my screen. She's going to talk about the task 2.3, which is focused on the interactions among flow, temperature, and biota. So let me stop sharing.
Okay, can y'all see that? Oh, do we have a question?
Yeah, we have a question from Kathy.
So I'm Kathy Buchanan. I'm with the California Indian Water Commission. And in the introduction, the only thing I heard was that this was a team of scientists that were put together for this whole thing. I just want to know, were any of the tribes in the areas invited to the table to discuss this project?
Yeah, Laura is she'll touch on that too. But that's a really important element and I'm glad you brought that up. And so yes, we are more specifically for the case studies in specific watersheds. We've been interacting with Paula tribe and they're getting us in touch with kind of the larger community of tribes within the region, but also statewide. And so definitely we want to continue to try to meet with different people and incorporate feedback and hear about different ways that the statewide framework and some of the tools that we're developing would be helpful and different resources, like in terms of the outreach and the materials that we're producing. One of the first tasks focus on outreach is kind of surveying different groups to understand what are some of the challenges and what are some of the materials that would be helpful for different groups. And so we're not going to talk about the outreach and training today, but yeah, that is definitely a key task, and I'd be happy to speak with anyone on this topic. maybe in a separate meeting. But really good point.
Any other questions before we go on? Okay. Thanks, Chris, for the setup. So I'm going to be talking about the specific project task of how changes in flow might be influencing the temperature in the streams and ultimately, of course, the biota, and how we can utilize models of these interactions to inform our ecological flows to account for water quality concerns, and in this case, temperature. So in terms of the tasks for this, in terms of the objectives for this task, we're developing a conceptual framework to guide our approach. Then we will be directly modeling the interactions between functional flows and temperature in relation to biota, and then ultimately providing refined ecological flow criteria to account for these interactions via pilot application in specific watersheds. So to go back to why this might be relevant is, as Chris brought up with the functional flow approach, is we know that maintaining as much of the natural flow regime as possible is very important. So too is thinking about the natural thermal regime in your river, which varies somewhat differently with the declines in the fall to winter period, and then a variable rise into the spring into summer peak. But of course, how flow might be impacting temperature is probably very variable depending on the season you're looking at. In that winter period, there might be a pretty weak relationship because air temperatures are declining, flows are relatively low or just flashy. And this has been reflected in some literature out there. Versus in the spring to summer period, there might be a stronger relationship because the rate of change in terms of your declining flow levels will influence how quickly the temperatures are going to rise, and then that summer base flow will likely influence your peak summer temperatures. So keeping all of that in mind, how do we actually approach this in the context of the functional flow framework? So thinking about how we can refine each of our functional flow metrics, which in one example might be the reference spring magnitude, which would be a range of values based on unimpaired flows. We might then think about, okay, what is the counterpart in terms of temperature? So what would be our reference, in a way, ideal spring temperatures? And this might be based on species data and making sure we're not exceeding their upper thermal limits. And by utilizing those two things, we can therefore look at models of flow, of temperature against flow, and then looking at the overlying reference FFM, in this case, the spring flood magnitude, and then comparing that against what is our upper temperature max that we need to consider, and therefore maybe need to adjust where our lower limit of reference spring magnitude needs to be. So doing that will ultimately result in an adjusted functional flow metric to account for potential temperature concerns. So it is important to recognize, of course, that there are other factors that are influencing our water temperatures, and we are accounting for this in our models. We're thinking of things such as elevation of the reach, drainage area, the slope, of course, canopy cover, and then hydrology, a key one being groundwater influence. At the end of this talk, I'd definitely love to hear if you all think there are other factors you need to consider, because of course there are always blind spots when you're thinking about these things. So in terms of the overall approach, what we've accomplished thus far is we've developed a conceptual framework for the analysis of flow and temperature. We have selected our study watersheds and begun data compilation. The next steps will involve developing those ideal temperature ranges, which will likely be based on a species envelope approach. So leveraging the existing literature for key species within those watersheds. And then the next step will be developing the models of temperature metrics and functional flows. And then if needed, and if possible, we'll bring in biotic data to try to further validate, refine those ranges. So seeing if we have observed data that can help inform this further, and then exploring what additional outputs for this task might be useful for application. So in terms of a workflow, this project involves developing these models to assess flow temperature relationships and then comparing that against these ideal temperature ranges, and then ultimately using that to refine our functional flow metrics. And then, if possible, exploring our outputs from these models against actual observed data, if it is available, to see if there are potential concerns or deviations from what we expected. And then another optional step would be sub-analysis at the microhabitat level, which would involve 2D hydraulic modeling. So I do want to get a little bit more into that first step of the actual assessing flow and temperature relationships. How is that going to look? So this will involve, of course, the compilation of temperature and flow data, QA and QCing that data, and then generating these temperature metrics and functional flow metrics, checking for temporal alignment. We want to make sure that those two data sets are as aligned as possible, and then checking for correlations between each of the metrics of flow and temp and assessing for potential significant relationships. And when significant relationships are found, those are the subset of metrics we're going to focus on building regression models for, while including key covariates that I previously mentioned. And then once we have those regression models, then we would continue on to the next steps of comparing that with the species thermal ranges. So in terms of the watersheds we're considering, there are two, both in North and Southern California. And in the north, we have the South Fork eel, which somewhat you might be well familiar with. It is a priority watershed due to current and future cannabis cultivation, and it is a habitat for many salmonid species, as well as the foothill yellow-legged frog. In the Southern California area, we have the San Luis Rey, which is a priority due to the potential of upcoming cannabis cultivation being allowed. And it is also critical habitat for resident steelhead and arroyo toad. So where are we at with the data for these two watersheds? So for the South Fork eel, of course, it's a data-rich watershed, as some of you well know, and we had the good fortune of talking with Eli Asarian, who has generously shared his compilation of temperature data since up to 2019 for the entire South Fork eel. And also there is a related LSBC flow model that we can leverage. And currently we're on the stage of gathering covariate data for this watershed. For the San Luis Rey, it's a slightly different story. There is actually a similar LSPC flow model, which is good because there's very little gauge data on this river. There is some temperature data that we've compiled from various agencies, although it is rather spotty. One of the issues being the San Luis Rey is fairly intermittent, and so there's a lot of dry periods. And we have been coordinating with several different groups in this watershed, including the Palo tribe, which we're hoping they will help us coordinate with other tribes. There are 5 within this watershed, as well as the County of San Diego and other related groups. So the next steps for this task are completing the QA/QC of the flow temp data, actually calculating those flow and temperature metrics, compiling covariate data, and then developing the models. In terms of the questions I have for you all is, how do you feel about our approach capturing the interactions of flow and temperature? Do you think there are ways to improve it? We're definitely open to hearing feedback on that. Are there other sources of data to be considering? And are there ways that our work overlaps with yours? And would there be any collaboration that you would be interested in? With that, I'm going to take some questions.
Laura, we have a couple minutes for maybe 1 or 2 questions. And if there's additional time at the end, we can kind of circle back if there's more questions or discussion. Yeah, Norman.
Hi, Chris and Lara. That's an incredibly ambitious part of your overall project. 2.3 by itself sounds like a major effort. And I guess my question is kind of way back, sort of at the high level. Um, if you go back to like you were talking about, Chris, the three-part procedure of the regular CEF approach,
Mm-hmm.
the the work that 2.3 here and maybe even the other parts, 2.1 and 2.2, are they more or less like some tools and techniques and some case studies of how to do part B of CEF, or does you
Yeah.
think that this is more like some kind of more global um, modification of CEF, or is this? To me it seems too
Um,
site specific.
yeah, so our goal is to develop an approach for Section B. Like if you're in a watershed, so you go through Section A and you get your unimpaired flows. If temperature is a concern in your watershed, how would you go about refining the flow criteria in Section B? And so we're developing kind of a technical approach where you could do that and kind of illustrating how this type of modeling could be used to in the context of CEF. But I think more broadly speaking, this type of analysis could be used even outside of CEF. When you're thinking about the interactions between flow and other water quality parameters, it might be DO, it might be some other water quality parameter that you're interested in. And this is kind of a starting point of how you could approach it.
Thank you.
I don't know. Did that answer your question?
Yeah, thanks.
Yeah, thanks. Um, we have maybe one more minute. Is there any other questions? And I will note that, so we presented on task 2.3. So in future meetings, we'll have the other groups kind of give updates and present on those tasks. Yeah, Kathy.
So my question, how big is the footprint that you guys use for the water to measure the flow of the temp and the temperature? Because I know watershed footprint is going to have a huge impact on the flow regimes. So how far back do you go from the center of the streams?
Yeah, Laura, do you want to talk about kind of where the temperature
Um,
loggers are set, or maybe the map?
yeah, so
Oh, or do you mean at a given cross section, like at a specific stream reach, where within the channel would you measure temperature?
Yeah, where within the channel would you measure the temperature? And what are and also how are I guess the stressors to the channel quantified or documented?
um, so I mean, we're leveraging existing temperature data, and so it's kind of up to the agency that did the monitoring about where they placed the loggers. And it does, from what I've looked at with the data, at least for the South Fork eel, it really varies between like deep pools to riffles. So there's a real variation in that, and it's a good point that you bring up to be thinking about like where was the logger put in place. That's not always necessarily clear in the locations, but we'll do our best to keep that in account because, of course, that's going to be an important factor. And then in regards to the covariate data that I think you're kind of referring to, we're leveraging GIS-based data to compile that. Yeah, I don't know if you have further questions in that regard.
No, thank you.
Awesome. Well, thanks so much, Laura, and maybe we'll transition on to our next presentation, which is all about river temperature modeling for unmonitored sites with Tempest 2 and large-scale applications in Southern California. And I will say, like, as we transition, as Daniel pulls up his slides, that we're really excited for this potential to fill a lot of the gaps in data and knowledge on stream temperature. And it's really hard because the data doesn't really exist, not like how streamflow data exists through USGS. There's just not a lot of information, and this is a really cool and exciting potential new data set that could be leveraged in our state. So with that, I'll hand it over to Daniel.
Yeah. Yeah, thanks for having me, and thanks for the setup. I couldn't have designed a better transition if I'd been trying to. Because that's exactly where I was going to start. So yeah, we were seeing in that last talk about some of those watersheds of interest had quite a lot of stream temperature observations throughout the watershed. The other one, it was a little bit spottier. And that's generally the problem that my work focuses on, including for applications in Southern California. So, of course, we're often concerned with stream temperature in a specific reach, or as mentioned, with like a deep pool or what have you, hyperlocal concerns, although my modeling cannot get at that. I think you need a calibrated model for that. Um, but in general, observations are sparse. My work with Scorp started in the Los Angeles area, so I took that as an example. Um, these are all of the observation points the USGS was able to pull together in a multi-agency data set that has a total of about 300,000 sites across the country. Although some of those only have a few days of data. And you can see there's often really not a lot. So if you're concerned with, even an entire reach in here, you very well might have no data to speak of. Local data sets can expand that a bit, of course, but it's still as mentioned, it's still a challenge. And so that's what my work focuses on, and we've been collaborating with Scorp on in Southern California, is trying to fill in that lacking data coverage. So this is kind of the end product of what I do, with modeling for systems where we don't have, or points where we don't have local stream temperature data to fine tune our models. So ungauged stream temperature modeling. And this is one demonstration of the end product. It's a 5-year snapshot of a 20-year model run for 70,000 sites around the contiguous US. I will say this is an older model version, so you can see some errors in there. But this is kind of my big flashy demonstration of the overall objective, which is to be able to really fill in that stream temperature data everywhere, without dependence on having a monitoring site just downstream. So the overall concept of the work we've been doing here is based on remote sensing of land surface temperature. And so this was a demonstration from here in Colorado, but the idea is that we're able to, if we look at like this land surface temperature image of a small tributary of the South Arkansas River, the stream itself is a few meters wide there. The riparian's area is about 50 meters wide. What we can do is, we have these satellite overpasses with land surface temperature, and we can see, like, if you look down this image, you can see the thermal effect of the stream. Is anyone else
I see
not
your
seeing the?
presentation.
You're looking at a slide that says the general concept?
Yeah, that's what I'm seeing too.
Okay. That's weird. I noticed that Zoom oh, you got it? Cool. All right, perfect. Yeah, so you can see, I mean, you can certainly see some topographic impacts and the like, but you can also see the stream itself in the thermal infrared, even from satellite. And that's the core of our modeling work is, of our historical estimation modeling work is using that satellite remote sensing to gauge what the stream temperature is, including for big rivers, small streams, urban areas, mountains, deserts, really anywhere. Is the idea. So the model we've been using in collaboration with Scorp in Southern California is called Tempest 2 for stream temperature estimation version 2. Version 1 was a monthly resolution version. So the important thing to know about the central thing about the model is that it outputs 1 kilometer resolution, so you can really look at a particular reach of interest, although not a particular pool of interest, daily mean and maximum stream temperatures, and it does that without the need for local observations. You can use local observations to fine-tune the model. Whether that will actually improve model performance or not depends on the period of record at the local sites. Sometimes if you have really short periods of record, it just gets confused. But with long periods of record, like in the South Fork Eel River, you could probably fine-tune the model. But it doesn't need those local observations, which means that it's a key advantage in those more sparsely gauged watersheds. The other side is that to make that straightforward to do, it's fairly minimal on data requirements, just land surface temperature, humidity, topography, and land cover. And we provide automatic data retrieval. Right now, that's through Google Earth Engine. Non-Google Earth Engine data retrieval is definitely something we could set up if depending on Google Earth Engine is a problem. And we provide a pre-trained model. So a big part of our focus here is that you just download data and go. We're trying to minimize the amount of setup and calibration and so forth. So that it's reasonably straightforward to actually use at scale. And just a quick overview of the way it works. I'm happy to loop back and elaborate, but I don't think it's necessarily essential in the interest of time. So it actually, interestingly, it's able to work only using data right around the point of interest. So very different from modeling the entire watershed. And then what we do is we separately predict seasonality, and then so the pattern of annual variation of stream temperature, the annual temperature cycle, and then how sensitive the stream is to short-term variations in weather. And then we're able to add those together to get a daily time series. And I was thinking in the previous talk that the way we approach seasonality is kind of like a backwards environmental flows framework. We sort of have a set of basic seasonality metrics that we're able to reconstruct the annual temperature cycle from, and then we model those and then rebuild the time series from that. So it can also, if you're concerned with a specific aspect of seasonality, it can just predict that aspect directly. But I think the big question with models like this is always, well, does it work? You know, if you're working without that local data, is it actually performing well? And generally, Tempest 2 estimates for ungauged sites have a root mean squared error of about 2 degrees Celsius. And these are our USGS validation gauges. You can see they're quite sparse in Southern California, but we do have a few. The Mediterranean part of California does have somewhat higher errors than average, but we still see most sites are in that 2-degree range, with the exception of some that are more in the high mountains or the desert in particular. We really have very few sites in Southern California, but they're also generally in that range with a few that are a bit higher up. And so that's its overall performance. I will note, really big reservoirs can cause problems for that. But that's more like the big Colorado River reservoirs and the like. And sometimes high groundwater activity causes challenges, but for most sites, it's not a huge problem. And then a different way of looking at it is just comparing predictions to observations overall. Generally, it captures about 90% of the total variance in stream temperature across sites and days. That's for daily means. At a gauge, it does a little bit better for capturing the variation in time. Daily maximum temperature does a little bit worse. And then you can aggregate it to something like monthly mean temperature and, of course, get better performance there. And part of that is that it's better at seasonality than it is at short-term variations. So if you're trying to capture longer-term stream thermal regimes, it does better. And then this is the distribution by space. So you can see the overall performance, the overall error range for Mediterranean. California is generally a little under 2.5 degrees typical errors. Low bias, though. It tends to be less biased for most sites in Mediterranean California than it often is elsewhere. But of course, that's all focusing on a very general overview. So the other question is, how does it do more specifically in Southern California, where we have maybe more than those like 3 USGS gauges that were over there? So we've been working with Scorp on the case study to validate it in the Los Angeles area specifically. And Scorp provided data for these validation sites in the Los Angeles and San Gabriel River watersheds. So we tested it out on those to see how it would do much more locally. I will note mostly these have shorter periods of record than the USGS validation gauges, so that does affect the comparison. And we've been looking at these with a focus on ecological targets, so seasonal ecological targets. So generally, this is modeled on the left and observed on the right. Generally, we get fairly good agreement between Tempest 2 and observed sites about whether a given site does or does not exceed a given ecological threshold. Of course, quite often that's pretty easy because it either always exceeds it or never exceeds it in reality. Yeah. But yeah, so in general, we do see that it works fairly well. Despite, I mean, depending on where you are, 2 degrees can be a fairly substantial error, but most of the time it doesn't actually cause it to miss whether a site is hitting a ecological target or not. If we look at the difference in predicted exceedance rates, we can see that it is usually fairly close to zero. Sometimes it can be that there are sites and thresholds where it can be completely off. It definitely struggles with whether the yearly maximum temperature is greater than 30 degrees or not. But overall, the differences between predicted and observed agreement rates are fairly low. Although that is quite variable across sites. We see some sites that have essentially zero disagreement across the board, and we see others that have patterns of higher disagreement. And we can see that in kind of the scatter on the comparison of modeled and observed. One thing that we looked at that may or may not be of interest is that we don't see a tendency in error one way or the other as we get closer to the coast. So the mouth of the Los Angeles River was down here at the bottom in space, and we really don't see a spatial trend, I think is a key part of that. So it tends to behave reasonably consistently wherever you're looking, and the big point of what this is for is more those large trend analyses. So it's a key factor that it doesn't see that spatial trend. So that's really that brings me to kind of what it's for, which is that we're focused on large, maybe relatively coarse resolutions of thermal suitability. So something like, of these 10,000 sites throughout Southern California, which ones tend to meet ecological temperature thresholds, or which ones that maybe have had a concerning historical trend for management purposes. So it's great for really filling in that data set to look at big trends, maybe if you're using it to develop some of those regressions for ecological suitability. It can be useful also for very fast analyses of fewer sites. If you have a couple hundred sites of interest, you could pull long time series for those in the space of a few hours, including data retrieval would be most of it. And then the other thing you can use it to look at is trends in space and time at large scale. So our sites over here tending to do badly, while sites over there tend to do well. And that also is a lot of our focus. And so we've been collaborating with Scorp, but we're generally very interested in making our modeling useful. So a big part of the question that that I always come to these with is, what can we do for you? If we could fine tune the model to produce specific stream temperature metrics, we're interested in that. Things like cumulative degree days, maximum 30-day or 7-day means or maxima, threshold exceedances like these. If it'd be useful for the model to output that, we're interested in building that in. I've heard of some interest in uncertainty estimation. So if something like an analysis of likely uncertainty in an area would be useful. or for instance, prioritizing locations where if you have if you're planning to add some new observations, that might be useful for prioritizing new measurements. We do want the model to be usable on its own, but we're also happy to provide data sets if those would be useful. And so we'd be interested in hearing about what sort of coverage might be useful if we were to provide a data set. A totally random hypothetical that definitely isn't on the next slide is every national hydrologic data set in Southern California from 2001 to 2024. I mean, in general, we're happy to help with that because it takes me a few hours work to provide a large data set for up to 10,000 points or so. And we are also working on developing a 1 kilometer resolution data set for the entire CONUS, although that'll be a little bit coarser because it's based on a grid and not specific points of interest. But that's something we're working on if that'd be useful. And um, I'd be delighted to hear ideas or requests. And so this is an example of what we've specifically been working on with SQUIRP, so on the left is that USGS multi-agency data set again, showing where there is or isn't coverage throughout Southern California. And then on the right is the exact predictions are not super important. I just pulled out overall maximum modeled temperatures for a demonstration. Is our 12,000 model points for, as I mentioned, every NHD location in Southern California. So this is really the kind of thing that we're working on being able to provide is these enormous expansions of data coverage that you can look at large scale trends. Like where does it tend to be cooler or hotter? Some of that's just going to be elevation, of course. Where might we see some big hot spots? And then, of course, this was a single image, but we can also look at things like what are the trends? Are there areas that are heating or cooling more or less? Are there areas where I would be interested to see how well this does for training, for fitting those correlations between flow and temperature that was talked about in the last presentation? I don't know that that's been looked at specifically with Tempest 2, so that would be an interesting thing to investigate. And then if so, that could serve to train, if it does well, that could serve to train those correlations um, at much larger scales. So I think I'm running a little short, but I think that's the quick overview. Yeah, thank you for having me. Any questions? And as I said, I'd love to hear any ideas or requests at that email address.
Awesome. Thanks, Daniel. Are there any questions for Daniel?
I have one question. Partly because they're in Southern California, but I also think about just the broader Southwest is like the dealing with the intermittency of your streams and like how could you, I don't know if that's something y'all are accounting for is like when necessarily is the model actually modeling just, the surface temperature and the flows aren't actually flowing, you know what I mean?
Yeah. Yeah, I think so. I mean, Tempest 2 will give you predictions if there's not flow, and then that would be something that you would have to separately account for whether there is or is not flow. It's kind of funny that way. I like to say it will, if you ask it for the temperature at the summit of Mount Whitney, it will tell you what it thinks it would be if there was a stream there. But I think it's yeah, during low flows, it should be able to get it like right in that transition zone to some degree because of how it affects the surrounding land surface temperature. But that is something you would have to model separately.
Gotcha. Thanks.
So if you had, I guess, observed or modeled stream flow, then you might want to overlay it with the temperature outputs and see like, okay, if it's zero flow, then you can kind of.
Yeah. Yeah, that's probably would be the best way to approach that.
Any other questions? I have a question. So you brought this up, thinking about other applications, and I think I would be interested in exploring the kind of thinking about the ecologically meaningful temperature metrics for different seasons and seeing how
Hmm.
that corresponds to the functional flow metrics. Um, yeah, so maybe we can talk a little bit more about that
Hmm.
um, in some of the watersheds that we're working in.
Yeah, absolutely.
And I think relating this back to the first presentation that Laura gave, one of the questions that we have our functional flow metrics that are
Hmm.
based on kind of the seasonal components of the annual hydrograph. One of the things we're thinking about is can we identify similar temperature metrics, like functional temperature metrics that
Hmm.
could be used as kind of a management framework in a sense. And so it's really cool to see that this data, like you can ultimately, if we come up with a set of seasonal temperature metrics that are related to the functional flows, we could essentially calculate some of those with the outputs because I think you would need daily
Yeah.
temperature data to calculate the metrics.
Yeah,
Um,
I've been thinking that would be interesting to look at. One of the items in my long list of potential spin-offs is what if you did a functional flows but with temperatures? And I think that is to some extent that kind of thinking is built into the model. Not
mhm.
as much with a focus on ecologically relevant here, but with the way we represent seasonality with a breakdown into like overall annual variation, and then the spring and summer anomaly here is essentially the spring snowmelt pulse and then the summer low flows. So like the magnitude of that thermal effect, as well as timing are kind of built into the model framework. So it'd definitely be interesting to look
Cool.
at that at scale, and tie that to ecological concerns.
Yeah. And then another thing that I was thinking about that we've talked about in the context of Ceph is like when you think about stream temperature, what is your management goal? Is
Hmm.
it specific species thermal tolerances? Is it can we have kind of an analog to the functional flows of using unimpaired? Like what would be the
Yeah.
unimpaired temperature regime that would be protective, like more holistically?
Hmm.
And I was curious if your model, this is current
Hmm.
altered temperatures. Could your model go back and predict, like based on if you change the land cover and some of your metrics back to unimpaired conditions, would it be able to predict unimpaired temperature?
Yeah. Yeah, so not as much this model, but our other model, that's more focused on forecasting, but it can also run historically. Is so because this model is based on remote sensing, it doesn't have a good way to disentangle like the urban heat island effect or what have you. Um, but our other model is based more on air temperature, so with that you could absolutely run like pre-urbanization or unurbanized air temperature and land cover, for instance. So that's definitely a possible use case there.
Cool. So that's is that model, is it a different model?
It's a very similar framework, but it is a separate model. It's in review right now. It's called Tempest Next. So but yeah, very similar overall setup. But yeah, that's definitely something we'd be happy to talk about looking at.
And then is the goal for that one like looking into the future changes in climate and kind of
That's more
yeah.
what we originally had in mind. Yeah. It's really its big focus is short-term forecasting, to support like real-time management work. Like we're going to have a problem 6 days from now. But it is built to support climate projections as well as disturbances. Disturbances Tempest 2 can do if they're actual historical disturbances. We've been using it to look at wildfire effects around the western US. But yeah, that's a lot of the focus would be looking at disturbances, and of course, you can then undisturb it to see what it would have been hypothetically.
Cool, thanks. Norman?
I had to step away for a few minutes during the Q&A, so I apologize if somebody else asked this question. In your training step, since you're using remotely sensed data, it seems mostly, are you able to tap into things like riparian density or anything like that that might have a bearing on stream flow temperatures, cloud cover, at the time of measurement, things like that? Or I don't know what all the scope of the training data is. You did mention some of it.
Yeah. So we don't explicitly look at cloud cover directly, but we found that it doesn't seem to actually have a huge impact outside of how it affects land surface temperature. So a lot of those patterns are proxied through the remotely sensed land surface temperature. We do look at the local abundance of water and forested land cover, but the more specifics there, and I know a lot of the like more specific data sets are harder to get at high resolution over long periods, so we try to avoid depending on those heavily, but a lot of that is proxied through land surface temperature. I've found that Tempest 2 is remarkably clever at catching impacts that it doesn't have any direct access to by way of how it affects the observed land surface temperature.
Right.
Lucian?
Hi, yes, good morning. Sorry I had to join late, but you mentioned that you were looking at some of the results from, in association with wildfire.
Mm-hmm.
And how has that been turning out? What have you been seeing?
So this is a very, very preliminary takeaway. The study's not in review yet. But the big thing we found is that for summer stream temperatures after a fire, the dominant effect is really the riparian burning more so than the entire watershed. Is really the dominant factor in whether you'll see significant increases in temperatures. Again, preliminary result, but yeah, that's really the biggest takeaway. The other big takeaway is that it's very dependent on everything else is very dependent on exactly which data set you look at. Um,
Yeah, of course.
But yeah, riparian zone seems to be the big one, riparian burning.
So if they can preserve those to some extent, which
Yeah.
typically happens, they seem to burn over.
Yeah, exactly. And that's so an example management would be like encouraging beaver activity to create those fire refugia.
Right. All right. Thank you so much.
Yeah. Thank you.
Kathy.
Can you include sediment flows in the wildfire areas in your model?
It doesn't have a direct way to represent them. It may see some of that effect because of how it changes the albedo of the water, and then knock-on effects on land surface temperature. But it doesn't have a direct way to account for it. Since it's I'm not sure if I actually explicitly mentioned that it's a statistical model. So it doesn't have a direct process representation like that.
Okay. Your new model that you're working on, the Tempest Next, is that what are the parameters that you're adding into that model?
Mostly it uses a similar set of parameters, except over the entire watershed. It switches land surface temperature for air temperature, and then it adds a lot of there's a lot more weight on because of the full watershed on precipitation regimes. And then it has somewhat smarter internals that allow it to be a lot more flexible. Mostly it's using similar parameters though. It's getting a bit more out of them.
Does it have the ability to change the surface type, like fully vegetated, deciduous, meadows?
Yeah, it uses to get at that kind of thing, it uses canopy density.
So in that one, you can actually change it when the canopy density changes from a wildfire.
Yes.
Okay.
Yeah. And we with Tempest 2 can as well. It uses it uses forest cover. So it can sort of get at that. Although we actually tried looking at canopy density and found in Tempest 2 post fire and found that it didn't make much of a difference. I think again because that's captured in the land surface temperature. But with Next, yeah, you would be able to change the canopy density for a fire, and that's a lot of why we used canopy density rather than forest cover, since that's more
Okay.
focused on disturbances.
Thank you.
Mhm.
Any other questions for Daniel? Okay, well, thank you so much, Daniel. Really great to learn more about the modeling that you're doing, and I think there's a lot of broad applicability to this group and what we're doing in California.
Hopefully. Thanks for inviting me.
Yeah. So with that, we're a couple minutes early, but if Claire is here, we can transition over to her presentation, which she is going to be talking about a watershed-specific approach to identify key functional flow metrics supporting the Scott River salmon reproduction.
I will share my screen. Hang on. Okay. Is that coming through?
Yeah, looks good.
Okay, great. Thanks for the opportunity to talk with this group. I'm Claire Koba. I'm a postdoc at Yale. I am still an affiliate at UC Davis, where I did most of this research. And I'm going to be talking about a paper that just came out this summer, as Chris mentioned. And thank you guys for I think this is a handy setup. This is a bit of a departure. This is not about temperature today, but it is about taking functional flows and sort of expanding applying them to a different set of observations, in this case, ecological observations in salmon reproduction. And the paper here that we're excited about is in Ecohydrology. It came out in August. It's open access and available, and we're sort of trying to get the word out about it. Sarah Yarnell was another key collaborator, and this dissertation work I did in Thomas Harder's lab, and also kept following up on as a postdoc. So although this work started a few years ago, we think it's relevant to ongoing regulatory activity in Scott Valley. So we'd be interested in folks' reactions and feedback. And I think just to sort of get straight to the point and spoil the punchline, a key question in this paper is how much salmon variation can we explain with flow? That's sort of a good way to frame all these graphs I will be sharing. Predicting fish abundance is a popular project. We have several, in the last 10 years, there are a fair number of examples in the scientific literature of forecasting short-term species outcomes in fisheries. And a hydrologist, you may ask, why is a hydrologist studying salmon reproduction? The answer is to make our hydrologic model more useful, to expand its utility in response to the public meetings and the stakeholder process that I was involved in during grad school. And the way I've been thinking about these questions is sort of how does management affect flow and affect fish as a sequence? And there's two links there. The first one we study with one set of tools, and the second link, how does flow impact fish or ecosystems, we study with a different set. The first link, how does management change flow? Our investigation tools, this is sort of a hydrological question. You can do a well pumping test to turn on a well and see how it affects the flow in the river if you assume, all other factors are equal. You can run a pilot project. There are active managed aquifer recharge pilot projects going on in Scott River and across the state, and monitoring the effects they have on the groundwater system or the stream. And you also have hydrologic models, the tool that we're using in this research. And hydrologic models, like every model, they have some shortcomings, but they are are very handy for asking basin scale questions and generating a rich landscape of options and trying to see what, run many different scenarios and see what your sort of range of options are. The second link here, how does flow impact fish or ecosystems, is, there has always been much interest and work on this question. As hydrologists, we were interested in, can we express this in terms of the recruitment for a single species? Can we zero in on the flows that mean the most to a certain fish or to species in this case? And then also, how important can this flow be? How much variability in fish outcomes could be explained by flow? Is it enough that, what is the weight we should put on flow management versus management of other factors like temperature or water quality or food resources or habitat restoration, etc. So there are a lot of possible methods to relate flows to fish. You could do your standard linear regression from high school algebra, where you plot x versus y and try to draw a line through the points and see if you can see if it makes a strong relationship. You can take it a couple steps more complex. And in this paper, we used two statistical approaches. We used lasso regression and MARS. And I'm happy to get into the details of those methods. But the biggest thing to understand about the first one, lasso, is that it penalizes model complexity. So the more predictors you add to your multiple regression equation, the more it penalizes that in terms of the equation that it's minimizing to find its ultimate prediction function. And this is good for high dimensional data, because if you have a number of predictors that approaches or exceeds your number of observations, you can just keep adding basically, noise until you achieve an overfitted model. So when you have yourself in that situation, and for functional flows, we have a lot of different ways of measuring flows, the number of predictors can be pretty high, and ecological observations are often, of limited sample size. Penalizing model complexity can be valuable to avoid overfitting. Another method that we used here that I won't focus on as much is MARS. This is an autoregression technique, which is where a time series of data, such as ecological observations, is used to predict itself, as well as incorporating covariates such as flow or alternative observation types. So I'm highlighting the lasso results for purposes of this talk, but I have all the results at the end if we want to ask questions about these two different techniques. The setting is the Scott River system in Northern California. In the inset map, the outline here is Siskiyou County. It's within the broader Klamath Basin. Scott River is a major tributary of the Klamath, and there is, the salmon runs in this river are of importance to the overall Klamath run. The data sources that we're using in the statistical modeling exercise, so we have a response variable, which we're trying to see how much variation can be predicted in the ecological observations. The sample size there is about 15 to 23 years. Due to, there's been a lot of investment in ecological monitoring in this river system. And the places where those observations are made are on this map. There's the fish counting facility where spawning adults are observed, and the rotary screw trap where outmigrating juveniles are observed. And those are the red diamond and the green square, respectively. The blue triangle at the top is the confluence with the Klamath River. And the predictors are the functional flows, which are calculated from the Fort Jones gauge, the yellow dot on this map, and the daily flow data from that key monitoring location. That's about an 85 year long record at this point. And so we tried a couple different flow calculators to really get a handle on this ephemeral system. It is undammed. It in average to dry water years tends to go dry in some parts of the stream system. And what we ended up using as our calculator was this work from this master's thesis coming out of UC Davis quite recently by Cam Carpenter. And the Scott River system, as many in this group are probably familiar, has this classic Mediterranean annual flow hydrograph, where in the dry season, we're down to like tens of cubic feet per second, especially in dry years, while the wet season has storms of thousands of cubic feet per second. And the spring recession is a key part of the hydrograph, as well as the wetting up in the fall. So to create the statistical, we need to build a table to run this statistical exercise. So we aligned annual functional flow values to the salmon cohorts. And this was slightly complicated because the same functional flow value, like fall of 2012, can affect two different cohorts of, for example, coho salmon. Perhaps one that is just about to be spawn or laid as eggs, and one that is overwintering as yearlings. So we used this schematic to align those functional flow metrics in different seasons to the age, the life stage at which the salmon cohorts were when they experienced that functional flow. So for coho salmon, there's a 2-year period. They have 2 rounds, or 8 seasons of functional flow metrics that influence their development in the freshwater system. And for Chinook, it's only 1 year. They only have 4 seasons. And our results, we could start by just summarizing the history of the Scott River in functional flows, starting with the total annual flow in the upper left here, which there's quite a bit of scatter. It's highly variable. It's a, California River, but there has been a persistent trend downward in total annual flow over the last 80 or 85 years. Something similar in the magnitude of the fall pulse, but it's sort of that's like not as obvious of a trend. The fall pulse onset has been trending later, although variability is also quite high, as has the onset of the wet season. So this is later in the water year that the wet season is beginning. The median base flow in the wet season has not changed much. The trend there is very slight. But in the spring, the speed of the recession is getting faster. So it's a steeper drop off now than 80 years ago. And then finally, dry season metrics, bottom left is the dry season median flow. So definitely the dry seasons the flows have gotten lower over time, of an average between 50 and 100 CFS down to, 10 to 50 in the 2020s. And then the duration has gotten longer of the dry season. So we have these, putting these pieces together, we see this picture of like increasingly difficult conditions for salmonids. You can also look at this not necessarily with functional flows, but with these simplified connectivity date metrics. Here on this example, it's the date at which the flow first rises past 20 CFS in that fall rewetting period, or 120 CFS as 2 examples. And then in the spring recession, the date at which they fall past those 2 thresholds as well. And if you plot those dates, you can see visually that the season of high flows in the Scott River is getting narrower, and that's a persistent trend. The trend is more marked in terms of the fall. The fall onset is getting delayed more rapidly than the spring is happening earlier, but in either case, the trend is pretty consistent. So that's just painting this picture of this history. So perhaps we can use that to say that managing flow and fisheries in Scott River, we're having less and less margin for error, and conditions are not favorable. Another thing you can do, so that's just looking at the predictors, just looking at the functional flows. Another thing you can do with our statistical big table that we were building with the ecological observations and the flows is to run a bunch of correlation coefficients, which we did. And that was just sort of an early step. And you can stare at these for a long time. The ecological observations are our 7 different types of observations those are the 7 columns for Chinook in the left 3 and coho in the right 4. And lots of different functional flows, as well as we included spawners as a possible, another thing to look at for correlation. And the big picture takeaway here is that there are many different metrics that really have no bearing or are not strongly correlated with a lot of observational or with a lot of different types of ecological observations. And the two different species don't have the same patterns. So they're influenced by different flows in different ways. And that's sort of that makes sense. We think this is a it's a multifactorial experience that the fish are having. It would be unusual if we saw only one really strong correlation coefficient. So the next part of our results, we tested 3 statistical model structures in terms of what the predictors, like what the units were of what we were trying to predict, and what the predictors were included. And again, I want to emphasize that the terminology here, prediction is just sort of jargon from statistics. This is trying to figure out how much of the variation in fish observations could be explained with flow, or in some cases with flow plus spawner abundance as an added variable to see if that would change the predictions. So we tested these 3 model structures with 2 methods, giving us sort of 6 different structures, and we ran each of those 6 for coho and for Chinook. So we have basically 12 different models. And then these are the statistical results. I don't want to walk us through every part of this, but the bottom line is that, for example, to predict the number of Chinook juveniles with this set of lasso results, we tried to find the value along the x-axis where this log lambda produces the lowest error value. So that's the top right graph. That's where that brown line is located. And then on the left, we have a set of the same graphs for coho smolt per female spawner. So we're trying these 2 different units of ecological observations, and we're running the same set of statistical modeling. The other important piece from this is that for these 2 example statistical models, we were able to explain 40% of coho smolt per female spawner and 60% of Chinook juvenile abundance based on that, minimum error model, where it seems like we're balancing model complexity and explaining the most variation possible with avoiding overfitting. So that resulted in a model with 3 predictors for coho smolt per female. That's just one example of the 12. And the 3 were the first flow reconnection date at 120 CFS, the second fall difference number, basically the fall flow increase for the second fall in the coho lifespan, and then the timing of the wet season onset as well. Although that, as you can see, that coefficient is quite a bit smaller. That means it was a smaller effect in this modeling exercise. For Chinook juvenile abundance, for this example, out of 12, there was only 1 coefficient that was not 0, indicating that this wet season median baseflow magnitude was of high importance, much more statistically important than the other flows. And the simplest model you could balance this overfitting versus explaining variation with just 1 predictor. Although in the series of other models, we found that this median base flow wet season magnitude, as well as spring recession, those both emerged. And then, so just to walk through the full set of results for these 2 examples, you can see for the top graph is for coho smolt per female spawner again. It only explained, again, 40% of the variation. And so visually, you can see these predictions, the black dots do not cover the full span of variation covered by the actual observations in the gold triangles. That's indicating that this model is conservative, and it is like, what portion of fish variability can we attribute to this flow, at least in this estimation? And so it's just sort of a visual reminder that there are other factors influencing these ecological outcomes. And then for the Chinook juveniles in this example, where it could explain 60%, there is a better visual match. So like the observed values are closer to the predicted values in the years when they both occur. So that is a quick tour of the methodology and some of these results. To summarize this empirical estimate, the highest importance flows that we found for Coho and Chinook were earlier and higher fall flows for Coho, although there is a wrinkle, which is that fall flows in their second season had a smaller but opposite effect on outcomes. And then for Chinook, lower wet season base flow was better for them and a slower spring recession for Chinook, perhaps indicating that they're really sensitive to storm flows or scouring or egg burial, and they benefit from, higher flows or a delayed or a longer recession period when they're trying to outmigrate. And I want to caveat that with this type of small ecological data set, these findings, like even as basic as which flows are more important, they're still highly sensitive to new observations. And so as we march forward in time, it might be valuable to just add more observations and rerun the same code that we used to generate these statistical estimates and see if these patterns persist. The correlation coefficients suggest that both flow and spawner abundance influence juvenile production, that it's not just one is very dominant. And around half a variation in fish recruitment, 40 to 60 ranging across those 12 different model structures, cannot be explained with flow without overfitting. So there's certainly, maybe that's a one rule of thumb to come out of this. Half of it might be explained with flow and the other half perhaps with other factors. However, with appropriate caution and accounting for uncertainty, we believe this approach allows us to take a hydrologic model, like the one we used to support the groundwater sustainability plan in Scott Valley, to analyze the changes in flow due to management, and then use it to estimate a fish impact in terms of how important flows changed for the whole model time period, including over water year types that are wet to dry and sort of cumulative effects over decades. And I would be happy to take questions.
Great. Thanks so much, Claire. That was a really great presentation. Norman.
I should put the article up. Anyone can ask me for the article link and I'll throw that in the chat in my time.
Oh, hey, Claire. I added it to the chat and I also added a link to the functional flow calculator.
Great.
For folks to use there because that's up on the TNC website now. Thanks,
Thank you, Sarah. I think I saw Norman's hand first.
Hi, Claire. Can you hear me all right?
Yeah.
That's a wonderful presentation of a very complex topic, and I like the sensitivity you expressed about overfitting a model, but I do have a question that might be a tendency to add more independent variables, if you want to call them those.
Sure.
I guess I'm really curious about year-over-year effects, especially with regard to pulses. Like large pulses are going to come down and reshape the channel and modify the gravel beds and flush out the organics and all kind of things that are going to have a huge effect on food webs, I would assume. And then you might expect that would show up, later, much later, perhaps that same summer, maybe, but possibly have some carryover effect. So I think your modeling, the lasso approach, you would treat each year as like it's almost a fresh start, right?
That's right. That is one assumption baked into lasso. They're all independent observations.
Right. Did you ever think about looking for year upon year carryovers effects?
Yes. So the Mars approach is designed more to suit that set of assumptions that that's the autoregression part that you're using the time series partly to explain, previous time steps to explain what happens next. We did not see as good of a fit in those models. It was a slightly different approach because there's no complexity penalty. We only used a single hydrologic covariate with the autoregression approach. So we just tested them all. We just tested all the functional flows against all of the ecological observations where we were using this autoregression approach. And in this system with this data set, we did not see a lot of evidence of autoregression in these ecological observations. That's a little unusual because there's a lot of like regularity, like a 3-year returning interval for coho salmon cohorts. So we would expect that. And we found that in one metric, but none of the other ones. But that's the only way in which we looked for year-over-year influences. If you're talking about like the influence of a specific storm, we have not incorporated any of that into this methodology. But I think, I don't know, it would be an interesting thing to think up a statistical design or an experimental design that would try to zero in on that.
Yeah. I mean, I even see nearby on the Trinity River a publication that talked about changes in the mayfly um, distribution. Which one? What's the one? The ones that armor themselves on the stream bed?
Caddis?
Caddisflies. Yeah, the alterations in caddisfly population uh, profiles based on pulse behavior. So there's
Okay.
clearly going to be some food web effects.
I'm sure.
Anyhow, thank you
Yeah,
very
and how
much.
long lasting is a good question. Thank you. I don't know who is next.
I think Kathy was next.
Okay, go for it.
Were diversions accounted for in the model, or can they be accounted for in the model?
I think with this statistical setup, so Scott River does not have major surface water storage. It obviously has surface water diversions for mostly irrigation, but those are somewhat distributed in space. The Fort Jones gauge is somewhat integrating all of the management that happens upstream of it. And so in that sense, perhaps like in dry years when the flow is particularly low, in the summer, it's an indicator that stream diversions are influencing stream flow at the bottom of the valley. But no, we did not include diversions as like a separate predictor variable or as their own data stream. I think I would be interested in what the data sources are available on that.
I mean, when flows are non-existent, there are no fish. And
100%. Yeah. No, I think the idea that you can draw a line between flow and fish really breaks down when the flows hit zero because like everything has to go to zero.
So do you know of any models that are accounting for the diversions?
Definitely a Scott Valley one from the Harder group has explicit. It's estimated based on crop demand, not on any recorded diversion records, but at a sort of water budget basin level, yeah, it accounts for surface water diversions on in terms of predicting flow conditions. It doesn't predict anything else. It predicts the hydrological setup, so the aquifer and the stream throughout the valley, but just the valley bottom covering the aquifer.
So where the salmon are in Scotts Valley, they're basically ignoring that area. I mean, because
yes, coho salmon, they
like,
really only they only spawn in the tributaries. Chinook are more likely to spawn in the main stem.
But if there's no water to get to the tributaries, they're not going to spawn. I mean,
yes, exactly. And the timing is really critical, and they need those spawning passage flows when their reproductive clock demands it. That's partly why the timing of the reconnection was one of the focuses in this set of predictors. The delays in when that connectivity occurs means that the salmon are waiting longer.
Okay, thank you.
Yeah, I'm happy to talk more if you have other thoughts.
Jen?
Thank you, Claire, for the great presentation. I wanted to follow up about coho, and you presented on kind of the most relevant predictors for coho adults. What can you speak to relevant predictors for coho juveniles?
I think, yeah, that might actually be flipped. The prediction units that we ended up focusing on for this exercise, they were all based on juveniles with the adults sort of incorporated in two of the model structures. So the sort of output, of the watershed, the response variable was the juvenile abundance as counted in that rotary screw trap. So these are all the flow metrics that we estimated for like predicting juvenile outputs and using that term predicting in this sort of like explaining variation sense. The adults, we did look at, you can say these correlation coefficients for this number of Chinook spawners and this number of coho spawners. I don't know if you can see my cursor, but interestingly, there was not a lot of highly correlated functional flows with the number of spawners. And perhaps all that means is that ocean conditions are very important in determining the number of returning spawners, as well as, the original size of the cohort. But the sort of dry season flows occurring before and the fall season metrics during their spawning, we didn't see a lot of highly correlated flow values. Does that make sense?
Yes, thank you. And sorry I missed that earlier.
No, I think it is a two different questions. It's like which flows are really critical at the spawning stage and which flows are critical for that whole rearing time period.
Thank you.
Yeah.
Any other questions for Claire? I had one question. You brought up the GSP, so the Groundwater Sustainability Plan.
Yeah.
So I was curious if you can kind of elaborate on that, and are there plans to integrate your models into the interconnected surface waters component of the GSP?
That's a long story. I will give you as short a version as I can. The Harder Lab was part of the technical team that supported Siskiyou County in developing their groundwater sustainability plans, not only for Scott Valley, but also Shasta and Butte. So they had 3 in Siskiyou County. And for that grant funded my graduate research for like 3 years. So I was directly, we were like going up and presenting at public meetings and running the model as like, look, this management scenario might have this effect on flow. So it was directly incorporated into the stream, interconnected streams component. It was, I believe, I don't think it's too strong a term. It was pretty cutting edge. We were using this model that had been in development for many years prior it was basically, they started developing it in response to TMDLs. So as Sigma rolled around, like they had this tool at this public university that they could suddenly turn around and use for Sigma. So we didn't have to invest a ton of time in model development. We could focus on a lot of scenarios. We ran like 40 or 60 scenarios, mostly influenced by stakeholder requests. And it was this, I think in my previous experience as a groundwater hydrologist, that's pretty rare to have that many different things that you can simulate. So I think the model is incorporated into the interconnected stream criteria in that it was used to say like how much stream depletion reversal was the goal. And the only way to really estimate that was with the model, because it's a really hard thing to measure in real time. So that's one answer. There's like a couple different nuances. I don't know if that answers directly your question, but there's I believe I think it will be part of the 5-year update as well.
Cool. It's really awesome to hear, and I love your presentation, and I'm really excited about the work you're doing. And
Yeah.
I think one of the questions that comes up in the context of CEF and functional flows is like, how do the natural ranges of flow relate back to specific species of management concerns, specific life stages? And I think this is a really cool study to kind of point at that.
I think we're aiming that's right. We're sort of a proof of concept of like, I've heard of top down and bottom up approaches, where top down is like the full natural flow regime, and bottom up is like trying to identify which functional flows are serving specific ecosystem functions. And so in this case, the way of estimating that is with like a linear relationship between flow and fish. So it's just one approach, but I think it's useful in that it is empirical. And its simplicity is perhaps like it is oversimplified. It doesn't account for population dynamics within the fish population. There are a lot of factors that are not included that we know influence fish outcomes, but its simplicity might make it easier to translate into other case studies.
Yeah, that's great. And one thing that we're working on is thinking about like what is the potential ecological risk as you deviate from unimpaired flows. And I think
Mhm.
something like this could fit in well with that to bring in another line of evidence.
For sure. Yeah. Although as Kathy mentioned, there are, this data set exists within sort of the envelope of where the observations are. And if you
Mhm.
get beyond that in terms of what you're simulating or what
Mm.
you're looking at for like climate change, then like all bets might be off. These relationships might be different at much lower flows or much higher flows or something. But
Yeah.
I agree. I think it's valuable to just sort of like step back and see what the data can explain. Thanks.
Yeah. Cool. Thanks, Claire. Um, do we have Yeah, so I think that's it for our presentation today. Thank you so much to our speakers. And I'll be posting if the presenters are comfortable, the presentations on our eFlows website on the meeting tab on the website, and then any other additional links like the papers and other resources that others can dig into and learn more about some of these efforts. Okay, so I think the last item that we have is I don't know if anyone has updates that they want to provide to the work group. You can kind of go around and give some updates. No, nothing. Okay. And the last piece is so our next meeting is going to be on February 10th, 2026, so in about 3 months. Are there any agenda topics or presentations that you know of or that you'd be interested in hearing about, whether it's the next work group meeting or it could be a subsequent one as well? Open to hearing any suggestions. So Melina Watts has a comment. She said, interested in hearing about relating historic flow to present flows. Yeah, that's a great, great question. And then we did have a presentation from Upstream Tech at the last meeting that was kind of getting at modeling flow alteration in impaired flows across the state. So I can send a link to that, but that's a really good topic to think about flow alteration and patterns of alteration across the state. Thanks, Melina. Any other topics? And if anyone can think of any presentations or any topics, oh, there we have one from Kathy. Awesome.
Yeah, sediment flows from wildfires.
Sediment flows from wildfires. Okay.
Yeah.
Yeah, it's a good topic. Any others? Yeah, so the agenda isn't set for the next meeting, so if anyone could think of anything or if you're interested in giving an update or a presentation to the work group, I'm happy to include you in on our agenda in a future meeting. And I noticed in looking at people's names that Alyssa Obester is online, and I just wanted to highlight that she's also a co-chair of the Environmental Flows Work Group. And so maybe at a future meeting we can have you like introduce yourself too. I don't want to put you on the spot right now. But she's here. She's a co-chair with Brianna from CDFW. And so just wanted to say hi.
Hi, thanks, Chris.
Okay, well, thank you so much. Thanks for the presentations and really good questions and discussion. And we'll see you all in February.
Thank you. Have a good afternoon.
You too.
Thanks,
Thanks.
Chris.
Thank you.